Good morning, everyone. Good morning. Good morning. How was the day? No, just now my day has started. Let's see how today would be. Yeah. So yesterday we have been discussed about hydraulic jump. I have asked you to solve this question. So I hope you might have solved this. If you have not also, don't worry. That's fine. Resistance. Give me a minute, please. There was some problem encountering. Let me check that once first. Yes. So now let's see. Yeah. Everything is ready for us now. Okay. So yesterday we have been discussed about a hydraulic jumper, and I have asked you to solve this question. There is a previous gate question, gate 2019 set to question. Now let's see how to solve this question. At the foot of the spillway, water flows at a depth of 23 centimeters. Water flows at a depth of 23 centimeters with a velocity of 8.1 meter per second. So, at the foot of the spillway, water is flowing at a depth of 23 centimeters with a velocity of 8.1. At the foot of spillway, I can find out the velocity as 8.1 meter per second and depth is 23 centimeters, which is 0.23 meters. Then from this, you can find out the discharge per unit width as V into Y. So 8.1 into 0.23. 8.1 into 0.23. So 1.863 meters square per second. So that I can know how much of flow rate is actually passing per unit. Okay. So what is the flow rate passing over here? Now, the flow enters as an M3 profile. You see, whatever this is nothing but M3 profile, right? So whatever this is an M3 profile. In the long, wide rectangular channel. So they mentioned that. So the channel is going to be a wide rectangular channel. A long mentioned wide rectangular channel with a bed slope how much? 1 in 1800 and Manning's is going to be 0.015. Okay. So the bed slope is given as 1 in 1800 and n is equals to 0.015. My dear, now you see at a certain distance, a hydraulic jump is formed at a certain distance from the foot of the spillway. So keep that in your mind. Now the hydraulic jump is not at 23 centimeters. The hydraulic jump is away from the 23 meters. This is M3 profile and this is the position where the hydraulic jump is going to be takes place. Where the hydraulic jump is going to be takes place. Now, assume the acceleration due to gravity G value is 9.81. Just before the hydraulic jump, the depth of flow Y1 is. They are asking the depth before the hydraulic jump. The question seems very easy. See, at foot of the spillway, they have given the velocity and the depth so that I can find out the discharge per unit. Now I know the discharge and I know the, means I want the Y1. Okay. So now you see for rectangular channel, you know that for rectangle, what is the relation between the conjugate depths? The relation between the conjugate depth means Q square by G is nothing but Y1 by 2 into Y1 plus Y2 by 2. This is the relation. Yes. But the biggest question here is I want Y1. What is Y2? What is Y2? You see, after the jump, if it is going to be happen, then it is going to be, see, a uniform flow or not? After the jump, it is going to be a uniform flow or not? Yes or no? See, whenever the jump forms away from the foot of the spillway, whenever the jump forms away from the foot of the spillway, mostly the downstream depth is going to be, normal depth, because once the hydraulic jump is going to be done, is there anything over here? You please understand the point I want to say here. So look, once the jump is going to be formed, this is going to be right. Once the jump is going to be formed, The flow is going to be uniform or not? Yes, this is a uniform flow. Once the jump is going to be formed, that's going to be the uniform flow. And before the jump, this is y1, and after the jump, this is going to be y2, which is going to be yn. Sir, how come you take it as yn, sir? Because there is no obstruction, my dear. For example, listen, for example, if this is a channel bed and there is a sudden drop in the channel bed, then there is a sudden drop in the channel bed. You know that whatever this line, there is going to be the serial. Let's take the slope as mild slope. Whatever this line, there is going to be the NDL. I hope you remember this, yes? So now the flow is going to be below the sluice gate or see whatever I'm taking the downstream side, the flow is going to be start and there is a hydraulic jump and the flow meets the flow is going to be start and there is a hydraulic jump like this and the flow meets the uniform flow. See, the flow meets the uniform flow and immediately you observe over here, due to this, right, due to the drop, water level will fall like this. Yes or no? Water level will fall like this. Yes. And in this case, if you see, this water level will not touch the NDL because it is a continuous flow, right? Now, in this case, the water level falls short of the NDL. The water level falls short of the NDL. In this case, whatever this y2 will be less than y1. Here this is y1 and here it is going to be y2 less than yn. So what is the difference between this one and this one, sir? See, due to this drop means if there is anything happening on the downstream side, haven't we discussed these things? Haven't we discussed these things? Yes. So if there is anything is going to be happen on the downstream side, then the water level may rise or may fall. But in the given question, there is nothing. So it is going to be assumed as a uniform flow. Now, the tile water level is assumed as a uniform flow, which means y2 is equals to yn. So the point is, it's all about knowing this one. Because I am ready with the equation, I have an equation, but I don't know what is the y2 value. Now for finding the y2 is equals to yn, you know, for a wide rectangle, if you remember, in the case of the wide rectangle, yn whole to the power of 10 by 3 is equals to q square n square by s naught. Have you remembered this? If you have remembered, means I have discussed this one in GVF. See, now I am applying the concept of the GVF also. Yes or no? When I apply the concept of the GVF, now I want y2. What is y2? yn. For finding yn is equals to, what is the q value I got? 1.863. Square into n value 0.015 square by s naught. What is s naught? 1 in 1800 whole to the power of 3 by 10. Now find out the yn value, please. Find out the yn value. The yn value is going to be 1.107 meters. The yn value is going to be 1.107 meters. Okay. So, Sir, why you are using the GVF formula as we are working about RVF? Arre Baba, I want YN, Nana. I want YN. How to find out the YN? How to find out the YN? See, I am not discussing about GVF. I am saying I set this formula in GVF. So how to find out YN? So this is the way you have to find out the YN. So what is Y2 now? Y2 is equals to YN. Now once you know the Y2 value, then Q square by G is equals to Y1 Y2 into Y1 plus Y2 by 2. Please let me complete this, then you can ask the doubts. So what is the Q value again? 1.863 squared by 9.81 is equals to Y1 into Y2 value is going to be 1.107 into Y1 plus 1.107 by 2. You send every other value to the other side. 1.863 square by 9.81 into 2 by 1.107. So from here I can write y1 square plus 1.107 y1 minus 0.64 is equals to 0. Now you can find out the y1 value. Y1 is minus b minus 1.107 plus root of b square 1.107 square minus 4ac. So minus of minus plus 4 into 0.64 into 1 by 2 into 1. 1.107 square minus 1.107 by 2. So the answer is going to be 0.419 rounded to 2 decimals, right? They're asking the question as rounded to 2 decimals. The answer is going to be 0.42 meters. You just observe, you see over here, the only one point that you need to know here is what is the depth on the downstream side. That's why as nothing, so no obstruction is provided. When there is no obstruction is going to be provided, what we do is on the downstream side, the tailwater is uniform flow. On the downstream side, after the jump, the tailwater is going to be uniform flow. Okay. Okay. Now, once I know that, then I need to find out the YN value. Okay. I need to find out the YN value. How can I find out the YN value? From the Manning's equation only, right? From the Manning's equation only, I can find out the YN value. Whether it is a GVF or RVF, whatever it is, if I say YN, what is YN? Normal depth. This is not the GVF formula. GVF means flow depth. YN means uniform flow. So from there, I can find out the YN and I substitute in this equation and I got the answer. Let me check out that answer. Yes, the answer is a 0.42. So I hope you are able to understand this. So can we assume 23 centimeters and H1 as alternate depths? Yes, yes, you can assume that. But no, you cannot assume that because both are going to be the supercritical, right? So you cannot assume that. Discharge will same after the jump. Yes, that's why we call it as a study, right? So in exam, how we will think the uniform flow concept? That's why I said no. No. Sir he asked the depth before the hydraulic jump. So no dissipation of energy. So can't we use a specific energy conservation, sir? If you use a specific energy, where is the velocity, sir? Where is the velocity? So the specific energies are same, but those depths are not alternate depths. You see, so one of our student is asking, sir, here up to this point there is no change in the total energy. Na? This is total energy. And here only it is going to be changes. So I know this 23 centimeters. I know this velocity. I have to find out this y1, right? So you can find out, but the point is here they are not the alternate depths. They are not the alternate depths. So as they are not the alternate depths, now let's see, let's solve that. Yes, they are not alternate depths, but E1 is equals to E2. Keep that in your mind. They are not the alternate depths, but they are E1 is equals to E2. Let me check that once. Give me a moment. One of our students has raised this concern. Let me check that once. I'm checking that. Give me a minute. No, it's not going to be possible. No, it's not going to be possible. It is not going to be possible. This form is not going to be possible. It will be possible only one way. This way is the only possible way. Can't we take y1 is equals to yg since y1 is just before jump and in M3 profile this indicates serial is crossing. No, my dear. No, see the serial is somewhere over here. The serial is somewhere over here. The serial is somewhere over here. See the jump. See you can observe over here. This is serial, right? The jump that doesn't up to this point. The jump will be formed just below the serial also because it's a reverse flow, right? It's a reverse flow. Okay. Now let's see the other things. So what's the use of giving jump away from the downstream? We are considering the tile water will be uniform only. In introduction, you explained with the weir example. What's the use of giving jump away from the downstream? We are considering tile water will be uniform. Are Baba, after the jump only the uniform flow is going to be happen. What's the meaning of tile water level? Tile means downstream. Do we have any relation between the specific energy at y1 and y is equals to 23? Yes, you can, but you don't get the answer. So because they're asking about the jump, right? So and they did not mention about forget about the see in the question anyway they did not mention neglect the frictional losses. In the question anywhere, they did not mention the frictional losses. So forget about that. So can we find yn by using q is equals to av? Yes. If E1 is equals to E2, then they are alternate depths, right? So need not be always the depths are alternate depths. Need not be the depths are alternate depths. In this case, if I would have said this is a horizontal, and if I would have said that frictionless, then I can say the E1 and E2 are same, but velocities are different, right? The velocities are going to be quite different, okay? Sir, we wrote the efficiency of jump. I think we wrote the relative loss. Please check once that both are same. Relative loss and the efficiency of jump both are same. Q value 1.863 only, right? That's what I substituted. Okay. I substituted 8.1 over here, right? So 860 square by 9.81 into 0.23 square into y2 square by 0.23 plus y2. Let me check this once again. I think I may have done something wrong. One point eight six square by 9.81, which is going to be 3. No, it's not going to be the value. That's going to be 10. That's going to be the value as a 10. So you cannot use this formula. You cannot use this formula. So you have to go with the other way only. So you cannot use this formula. I have checked with this. So there is no possibility of this one. If you solve this one and you can get, then you let me know, because I don't want to waste much more time for that. Yeah. So, so yes, when I thought initially after the jump, I told you the flow is going to be uniform. This is the one I mentioned here also. But if there is a drop like this, then y2 is going to be less than yn. So, converting given is equals to T2 and solve. No, it won't be coming. We consider the frictional losses in case of GVF, so we cannot equate the energy. Yes. So in the case of the GVF, we have considered the frictional losses, right? This M3 is C. You see, whatever this M3 is GVF. In the case of the GVF, we did not consider we consider the frictional losses. Yes. So when we consider the frictional losses, you cannot equate E1 is equals to E2. You cannot equate E1 is equals to E2. So that's the reason why it won't come. Why are we not getting an answer if we use specific energy concept? Because this is GVF. In GVF, we consider frictional losses. So when I consider the frictional losses, E1 is not going to be E2. E1 is not going to be E2. While deriving specific force, we consider the friction loss as 0, because I told you in the hydraulic jump zone, the length of the hydraulic jump is very less, so friction losses can be neglected. Remember, they should be alternate depths. Please keep that in your mind. The alternate depths means one should be subcritical, other should be supercritical. Are you saying those are going to be sub and super? No. There is no range for answer. They are asking rounded to 2 decimals. Directly, you have to find out the answer. Sir, can we find it what distance the jump is forming? Any process for that? Yes, there is there. You can find out the length at which the jump is going to be processed, but you don't require that concept. Okay, you don't require that topic. This is with the previous gate question. So gate 19. The point you need to know is when they don't mention anything as a tailwater, means after the jump you need to assume it as a uniform flow, and you need to find out y2 as a yn, and from there, after finding the yn, you can find out the initial means pre-jump depth y1. And apart from this, let's see if there is any other questions left over. Yes, you see a partially open sluice gate, discharges water into a rectangular channel. Now the tailwater depth is given in the channel is 3 meters. The tailwater depth means y2. So, and Froude number is 1 by 2 root 2. If a free hydraulic jump is to be formed at a downstream of the sluice gate after the vena contracta, of the jet coming out from the sluice gate, the sluice gate opening should be, see, they are asking that if this is a channel bed, keep that in your mind. Now, a partially opened sluice gate. So this is a partially opened sluice gate. Okay. Now, what happens is a hydraulic jump is formed at downstream of the sluice gate after the vena contracta. So first, flow will decrease, and you know the meaning of vena contracta. The vena contracta is a section where the flow is going to be minimum, and from here itself they are saying, see, clearly they are mentioning after the vena contracta. Yes. So now after the vena contracta, they are saying the hydraulic jump is going to be formed like this. That hydraulic jump is going to be formed like this. Yes or no? Now, whatever the tailwater, they are not saying the hydraulic jump forms away from the vena contracta. Did they? No. They are saying the hydraulic jump formed at the vena contracta. Means just after the vena contracta. Okay. Now, whatever the tailwater depth they mentioned, y2 is equals to how many meters? 3 meters. And you see the Froude number 1 by 2 root 2 means less than 1 or not, and FR2 is equals to 1 by 2 root 2. FR2 is nothing but 1 by 2 root 2. So now what they are asking is what is the depth of opening? So whatever this, let's take it as a y dash. The sluice gate opening should be, if the coefficient of contraction they mentioned is 0.9. So if I take the vena contracta depth as y1, because the jump is forming just after the vena contracta, so this is y1. Okay. Now what is vena contracta? Means what is the coefficient of contraction? I told you earlier while I was discussing there, the coefficient of contraction, if you go back, yes. So you see the coefficient of contraction, vena contracta, is nothing but area of vena contracta by area of opening. But here I said this is M3 profile. But there in the given question, I am mentioning you in this given question, I am mentioning you the hydraulic jump is forming in the given question, the hydraulic jump is forming just after the vena contracta. Okay. So now What is CC? Area of the vena contracta. Area at the vena contracta by area of opening, which means y1 into 1 per unit width by y dash into 1. This is vena contract, means quotient of contraction. So if I know the y1, then I can find out the y dash. So y dash is nothing but y1 by cc. So first of all, find out the y1. So as y1 and y2 are conjugate depths, these are conjugate depths or not? So from the FR2 concept, now I have FR2. When I have FR2, now can I use one relation? The means sequent depth ratio is there or not? That is y2 by y1. But if I can write this one as y1 by y2 minus 1 plus root of 1 plus 8 FR2 square by 2. So y1 by y2 is 3 meters minus 1 plus root of 1 plus 8 into 1 by 2 root 2 whole square by 2. So from this, y1 is equals to how much? Please tell me. 1 by 2 root 2 whole square into 8 plus 1 minus 1 by 2 into. So y1 is nothing but 0.62. y1 is nothing but 0.62. Now what is y dash, sir? 0.62. You see, from here, y dash is nothing but y1 0.62 by cc as a 0.9. So this is going to be 0.69 meters. What if they would have mentioned the coefficient of discharge? No, they won't mention the coefficient of discharge because the coefficient of discharge will be useful in the case of finding the discharge. That is different, okay? So if they would have given the quotient of discharge, see in the same question, if they would have given the quotient of discharge, the equation would be different. The equation would be different. So don't worry about that, okay? Now, I hope you understood here. If I would have given the C means in the same question, if CD is mentioned, then Q discharge is equals to CD into area into root of 2G H, where H is head of water from center level. So instead of FR2, they won't give the FR2 then. They won't give FR2 at that point. So they wouldn't give the FR2. Instead of that, they would give the water level over here. So with respect to center, whatever this water, that we are going to discuss in the case of the flow measurements. So don't worry about that. For the ESC, for gate point of view, you don't worry about that. For gate point of view, you don't worry about that. So this is the head of water now. This is the H. H is nothing but a head of water above the center level. Above the center level. So don't need to worry about this. Hope you understood. So what is the y1 value? Y1 is going to be the 0.62. Now that's all. Now you see there is also one more question. This is a previous gate question. Yeah. So in a lined rectangular channel, the Froude number of the incoming flow, see whenever the Froude number is more than 1, that is nothing but the supercritical flow. Yes. Hydraulic jump forms when it meets the pool of water. the depth of flow after the jump formation, the depth of flow after the jump formation is 1.51 meters. The depth of flow after the formation is 1.51 meters. Froude number of the flow after the hydraulic jump. So what is the Froude number of the flow after the hydraulic jump? They're asking the FR2. So in a rectangular channel, the Froude number of incoming flow is 3. A hydraulic jump forms when it meets the pool of water, and the depth of flow after the jump formation. After the jump formation means Y2 is going to be 1.51. Froude number of the flow after the hydraulic jump. So they're asking the FR2. So, but we have FR1, and from the FR1 we can find out the Y1. From the FR1 we can find out the Y1. Yes. You need to apply two equations over here. You need to apply the flow means two equations. So as they are asking the FR2, so how to find out this FR2? That we need to look. So in order to find out this FR2, we need to find the first Y1, and Y2 by Y1 is equals to minus 1 plus root of 1 plus 8 FR1 square by 2. So what is Y2? 1.51 by Y1 is equals to minus 1 plus root of 1 plus 8. 1 plus 8 FR2 square. What is FR2 square? Sorry, FR1 square. 3 square by 2. So from this you find out the Y1. 8 into 3 square plus 1 minus 1 by 2. So 1.51 by answer. So Y1 is going to be 0.4 meters. But I am asking you the Froude number after the jump, right? Sir, why you are solving this one? Because I don't know regarding to the, see, if I want to find out the FR2, I require at least velocity or discharge, right? If I want to find out the FR2, I require at least velocity or discharge. Yes. So now once I know the Y1, now I use this relation. Y2 by Y1 is equals to minus 1 plus root of 1 plus 8 FR2 square by 2. So now, what is Y2 by Y1? You can directly equate these two. You can directly equate these two, but so what is Y2 by Y1? Y2 now 1.51 by 0.4 is equals to minus 1 plus root of 1 plus 8 FR2 square by 2. Or you can use one more equation, Q squared by G is equals to 2Y1 square Y2 square by Y1 plus Y2. You use Y1 and Y2 and you find out the discharge. Once you know the discharge, then you can find out the FR2. Okay, so now you see, so solve this one. 1.51 by into 2 plus 1 square minus 1 by 8. Okay, sorry. This is not Y2 by Y1, this is Y1 by Y2. Y1 by Y2. Okay, Y1 how much? 0.4 by Y2 1.51. 0.4 by 1.51 into 2 plus 1 square minus 1 by 8. So the answer, Froude number FR2 is equals to 0.409. So you can take it as a 0.41. The answer is going to be C. Or other way, this is one way. This is one way. This is one way. Or I can go with the other way also. Or Q square by G is equals to Y1 Y2 into Y1 plus Y2 by 2. Okay. So now you know that I want FR2. FR2 means V2 by root of G Y2. V2 by root of G Y2. FR. Okay. Now I can write this V as V2 as a Q. I can write this V2 as a Q. Okay. Or FR2 square is equals to V2 square by GY2. And I can write this further as Q square by G into Y2Q. Can I? Can I write like this? Yes or no? So now I can find out this FR2 square, and from there I can find out the FR2. So, but why I am doing this one is if you observe, this is Q square by G R naught. So now Q square by G find out. So Y1 I have a 0.4, Y2 1.51, 0.4 into 1.51 into 0.4 plus 1.51 by 2. So what about this value? 0.4 into 1.51 into 0.4 plus 1.51 by 2. So this value is going to be 0.7576. Now you substitute 0.576 by Y2 cube. What is Y2? Y2 is given as 1.51 whole cube. So this is going to be 0.167, but I want FR2, right? So FR2 means square root of 0.167, which is equals to 0.409. So you can get it as a 0.4. This way or that way, I can go with this equation. And once I know the Q, I can find out the velocity. I can find out Froude number R. I will modify this FR2 so that I can find out this Q square by G directly. This Q square by G is nothing but 0.576, right? And what is Y2? 1.51. So what I got is FR2 square, then FR2 is nothing but 0.41, which is easy. This one or this one. You see here only one step, it will be complete. So I am using both the relations so that I can find out the Y1. See, the hydraulic jump concept is very, 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 very important. Keep that in your mind. Why I am taking Y1 by Y2 is go see, I need to find out FR2, right? If I write the denominator Y1, this is FR1. If I write denominator Y2, this is FR2. Earlier I know FR1, Y2, I find out Y1. Now I want FR2. So I am writing Y1 by Y2. So what about Y1 by Y2 is equals to FR2 by FR1 whole to the power of 2 by 3. You can write that also. Yes. Very good, very good. Now, for relation between relation between any depth other than alternate depths. And a Froude number. Have you remembered this? Yes. So any depth other than Froude number means then I can use one equation, y1 by y2 is nothing but fr2 by fr1 whole to the power of 2 by 3. So this equation can be used for conjugate depths also. Conjugate depths also, because you see in the case the relation between any depth other than the alternate depth. See, you take any depth other than the alternate depths, I can use this relation for the rectangle, and that too for the rectangle. Now, first of all, I need to know y1. Once I got the y1, see, everything I require y1. Without finding the y1, I cannot find out. Without finding the y1, I cannot find out, because they have given only the incoming flow Froude number and outgoing flow the depth. So now from the same equation I can use, so what is y1 please? 0.4 by, what is y2? 1.51 is equals to FR2 by 3 whole to the power of 2 third. Now what is FR2? 1.51 whole to the power of 3 by 2 into 3. So again this is going to be 0.409. So I am giving you multiple procedures. I am giving you the multiple procedures so that you can go with whatever the way you want. But definitely, if you want to find out that FR2, you require the Y1. So without knowing the Y1, you cannot find out this. So either you can go with this equation, or you can go with this equation, or you can go with this one. See, I don't remember too many formulas. I know one formula. I'm crisscrossing. I want FR2. If I want FR2, see, this is the equation. If I want FR2, do I know Y1? No, but I know FR1. So from this equation, I know FR1, I can find out the Y1 and I substitute this. Once I know Y1 only, see, once I know Y1 only, all these procedures are going to be useful. Once I know Y1, I can use this relation, or I can use this relation, or I can use this relation. Without finding Y1, you cannot use any other relationships. Okay, fine. Now let's see. Let's see this question. A hydraulic jump takes place in a frictionless rectangular channel. A hydraulic jump takes place in a frictionless rectangular jump channel. The pre-jump depth is YP, and the alternate and sequent depths corresponding to YP are YA and YS. See, the simple is there is a hydraulic jump. Okay, so whatever this depth, the pre-jump depth they are mentioning as a YP. Now, for this jump, the alternate depth is going to be YA and sequent depth is going to be YS. Yes or no? You know, YP and YS are sequent depths. YP and YS are sequent depths because the same specific force. But YA and YP, this is nothing but frictionless. I am mentioning the frictionless. So when I mention the frictionless, then you see here the water level. YA and YP both are same, means YA and YP are the alternate depths. YA and YP are the alternate depths. Okay. So once I know the alternate depths, now you know what is the relation between this? The relation is YP is less than YS is less than YA. You know that the alternate depth is more than the sequent depth or not? I sent you one point in hydraulic jump. While doing so, due to eddy losses, the water level falls short of its alternate depth, known as sequent depth. Yes. So this is the answer, option B. These type of questions can be expected in the IES also for this one. Yes, you see, what are the assumptions? See, in EAC 2019, what are the following assumptions that are made in the analysis of the hydraulic jump? What are the following analysis that are made in the analysis of the hydraulic jump? Means assumptions I am asking you. It is assumed that before and after jump, the flow is essentially two-dimensional and the pressure distribution is hydrostatic. Yes. I told you before and after the hydraulic jump, the flow is static and it is pressure distribution is hydrostatic. Yes or no? If you want, you can go back and you can check the assumptions I made. Flow is steady, pressure distribution is hydrostatic. I neglected the frictional resistance. I neglected the driving force. One is correct. The length of jump is so small so that the losses due to friction on the channel floor are small and neglected. So the length of the jump is small, so that the losses due to friction on the channel floor are small and are neglected. Yes, 2 is also going to be correct. 2 is also going to be correct. Okay. Now, third one, the channel floor is horizontal or the slope is so gentle that the weight component of the water mass comprising the jump is very high. The weight component of the water mass comprising the jump is very high. Actually, it should not be high, it is very less. Give me a minute. Yes. I'm sorry. I'm sorry. Here, in the first statement, yes. In the first statement, you see here one more point we're missing. See, the pressure distribution is hydrostatic. Okay, fine. This is correct. The pressure distribution is going to be hydrostatic, but it is not two-dimensional. It's a one-dimensional. We are taking only one dimension, right? We are not taking the pressures in the two dimensions. We are taking only the one dimension. So the point here is it should be one dimensional. It's not two dimensional. The flow is one dimensional. We are taking the flow only in one direction. So along the length direction only we are going to take, right? The flow is going to be one direction. The hydrostatic, but the flow is going to be only one direction or one dimension. So I'm sorry. It should not be two dimension. So the one is going to be wrong and two is going to be correct. The channel floor is horizontal or the slope is so gentle that the weight component of the water mass comprising the jump is very high. No, you know that in the case of the hydraulic jump, we take FD0 and FR is equals to 0. Yes. So they are mentioning a weight component is going to be very high. So it is not going to be possible. Weight component is going to be very, very less because as a theta is equals to 0, FD, what is the meaning of weight component of water mass compressing the jump? That is nothing but driving force. That is nothing but the driving force. So it is not going to be correct. Then what is the only option? The only correct answer is going to be 2. I'm sorry. They don't mention that point. Flow is one dimensional. Yes. Okay. Now, you see, so in some of the people in ESC, what type of questions they can ask is they'll ask you the type of jump. You know, based upon the inlet Froude number, we have discussed about the type of jump, right? So now you see, hydraulic jump forms in a horizontal rectangular channel carrying a unit discharge of, you see the units please. What is units? Meter cube per second per meter. 1.019 meter cube per second per meter at a depth of 101.9 mm. 101.9 mm. What is the meaning of 101.9 mm? 100 mm means what is the 100 mm? Please tell me. 0.1 meter, right? So this is nothing but I can write this one as 101.9 mm means 10.19 centimeters or 0.1019 meters. 0.1019 meters. Okay. The jump is classified as. So you know that hydraulic jump forms in a rectangular channel carrying a unit discharge of 1 point. See, these are rectangular. Okay. The depth is going to be 0.109. So what is FR1? V1 by root GY1, or you know that here you can find out the velocity. The jump is classified as. So instead of finding all these things, now let's see the Froude number root of GY1 or FR square. I'll go with the FR square so that I can write Q square by GY1 cube. We need to find out the range. That's it, right? We need to find out the range. So now if you observe the velocity, what is the velocity here? Please tell me. What is the velocity? Velocity is nothing but Q by Y1. Yes or no? So 1.019 by 0.1019, which is going to be 10, right? 10 meter per second. You see, observe here, this is 10 by root of 9.81 into 0.1019. I don't know the value. See, I am not using any calculator. I don't have any calculator. But you know very well, this is root of 9.81 into 0.1019. Array, forget about 1019. Forget about 1019. Root of 9.81 into 0.1. What is a 0.1 into 9.81? What is 0.1 into 9.81? The 0.1 into 9.81 is nothing but 0.981. Yes or no? 0.981 is less than 1 or not? Yes or no? So obviously this value is going to be more than 10. Will you accept or not? This value is going to be definitely more than 10. Why, sir? Now you see, sir, 9.81 into 0.1019. If I solve, that is going to be 0.999 and root is going to be 0.999. Exactly, this is going to be 0.999. This entire value is going to be 0.999. So it is going to be just more than 10. It is going to be almost equals to 10. So I can say this is going to be almost equals to 10. I don't have a calculator. So as I don't have a calculator, I don't solve. So 9.81 into 0.1, which is 0.981, I can assume it as a 1. So root 1, 10 by root 1, which is going to be almost 10. And when the Froude number is greater than 9, we call it as a strong jump. Yes. So what is the answer here? Answer is going to be B. Now, see, this is ESC 15. I am going to see the errors would be there. That error analysis we will be discussing in fluid mechanics, flow measurements. And this is that. Yes. So now again, this question, there is a hydraulic jump. I want to find out. A hydraulic jump occurs at the toe of a spillway. A hydraulic jump occurs at the toe of a spillway. And the depth before the jump is a 0.2 and the sequent depth is a 3.2. The depth before the jump, y1 as a 0.2 meters. Sequent depth is going to be 3.2 meters. And what is the energy dissipated? What is the energy dissipated? Energy dissipated means y2 minus y1 whole cube by 4 times of y1 into y2. 3.2 minus 0.2 whole cube by 4 times of 3.2 into 0.2. Okay. So we don't know the values. So that's the answer is strong jump, my dear, for the previous question. So 3.2 minus 0.2, 3.2 minus 0.2 is 3, right? What is the 3 cube? 3 cube is nothing but 27. Yes, by 4 into 3.2 into 0.2. So 4 into 3.2 into 0.2. So we need to find out this value. Come on. without using the calculator. So I mean I want to go with the other way. 0.2, so which is going to be 270, like, or 0.2, 4 into 0.2, 0.8, 3.2 into 0.8, or 3.8, it's 16, it is 24, 25, so 2.56, 27 by 2.56, it is going to be just more than 10. It's going to be just more than 10. Yes or no? It's going to be just more than 10. So 2.27 by 2.56. See, 2.56 tens means 25.6. Yes or no? 2.56 into 10 is going to be 25.6. And this 27 is just more than 25.6. So this is going to be just more of 10. So from options, the answer is going to be 10.5 because it's not 27, it's not 42. For 15, it is going to be more value. 15 into 2 is 30. So it's not more than 30, it's less than 30 only. The answer is going to be 10.5. See, keep that in your mind. In ESC, never ever you are going to get down the exact values because I don't have calculator. If I don't have a calculator, how come I solve this? I will go with the minimum calculations what I have. I'll go with the minimum calculations what I have, and then I substitute and I'll go with the nearby answer. What is the nearby answer here? 10.5. Yes. You see, when water flows through a long stretch of narrow rectangular channel, the water surface at the walls is higher than that of a central axis. Yes. You know, this is a water surface. When water flows, I told you the water surface at the walls is more than the water surface at the center. Yes or no? This is a wall and this is a center level. Yes or no? I hope you remember this. This is due to presence of the secondary currents and a side boundary friction. Due to presence of the secondary currents, and boundary friction, presence of the secondary currents and boundary friction. So we are going to see, due to presence of the secondary currents and boundary friction, water level on sides rises by pulling down central water level. And there is effect of surface tension also. Resistive effort of atmospheric air is felt more at walls than the wall. I said you the wind resistance or air resistance is insignificant. So you know that assertion is true. When water flows through a long stretch of narrow rectangle means effect of the secondary currents and boundary friction is more. So assertion is true, but resistance of air means wind resistance is neglected. I told you it's insignificant. So A is true, but R is false. And these are subject questions. Yes, with this we have covered all the different type of models regarding to the hydraulic jump. So in ESC we covered how to find out the type of jump, how to find out the head losses, and in gate questions if they don't mention anything on the downstream side, we assume it as a uniform flow. We can find out the initial depth, we can find out the coefficient of contraction, we can find out the inlet Froude number, we can find out the outlet Froude number. But basically what are the equations that have been used in the entire hydraulic jump? How many equations have been used? 1, q squared by g is equals to y1 y2 into y1 plus y2 by 2. 2, sequent depth ratio y2 by y1 is equals to -1 plus root of 1 plus 8 fr 1 squared by 2. That's it. And based upon those two only we have derived everything. Yes. And how I got this q squared by g is equals to y1 y2 into y1 plus y2 by 2 by equating the specific forces. So in 2020, in GATE 2020, keep that in your mind. In GATE 2020, 2 marks question in GATE 2020, 2 marks question came for the triangular channel, the same question. The same question, see what I'm showing you here, the same question, but in GATE 2020, they have given GATE 2020, they have given Y1 and they have given Y2. They are asking the discharge. They have given Y1 and they have given the Y2. They are asking the discharge. In this question, I gave the discharge, I gave Y1, I asked Y2. Yes or no? So in GATE 2020, they gave Y1 and they gave Y2. They are asking the discharge. That we'll be discussing at the end. And in the recent years, especially in both ESC and GATE, from 2018 onwards, most of the question are asking on the hydraulic jump only. 2018, 2019, 2020. So in GATE and IES, they're asking more towards the hydraulic jump. So you take the hydraulic jump concept more serious. The concept is very less, but the number of questions that you can explore is going to be more. I hope you understood the hydraulic jump well. So now that's all with the classroom practice questions, and now the only one topic left over. See why I'm that only one question, and in such, that is such, and that was asked long back in GATE and ESC. The last topic is known as surge. Yeah. Now surge. Surges. The meaning of surge is it's a unsteady, non-uniform, rapidly varied flow. It is an unsteady, non-uniform, rapidly varied flow. See, what is a hydraulic jump? What is a hydraulic jump? It is a steady, non-uniform, rapidly varied flow. And what is when does a hydraulic jump occurs? When does hydraulic jump occurs? When supercritical flow meets the subcritical flow, then the hydraulic jump is going to be occurs. When the supercritical flow meets the subcritical flow, then the hydraulic jump is going to be occurs. Okay. So now coming to the surge, it's an unsteady, non-uniform, rapidly varied flow. It is an unsteady, non-uniform, rapidly varied flow. Okay. So it is an unsteady, non-uniform, rapidly varied flow. Forms. But how it is going to be formed? Formed by sudden operation of gates. Sudden operation of gates. So you know that the non-uniform, unsteady nature comes by sudden operation of the gates. Yes. So by sudden operation of the gates, so the surge is going to be formed, and this surge is also known as moving hydraulic jump. Moving hydraulic jump. So the surge is also known as a moving hydraulic jump. Keep that in your mind. And moreover, my dear, whatever this surge is there, and whatever the analysis I have made in the case of the hydraulic jump, right, means the assumptions I have taken, the some of those assumptions will be applicable here also. Some of those assumptions will be applicable here also. So as it is a moving hydraulic jump, we neglect the frictional losses and we consider the eddy losses. We consider the eddy losses. But does the flow is going to be steady or unsteady? Does the flow is going to be steady or unsteady? Unsteady. Now, whatever the equations are I mentioned earlier, conservation of mass, continuity, conservation of energy, Bernoulli's, conservation of momentum, linear momentum principle. All those are three principles are for steady flow. They are not for the unsteady flow. They are for the steady flow. And that steady flow, for those things only, those are going to be applicable. And for the unsteady flow, you have to convert this unsteady flow into, whom? A equivalent steady flow. So as you cannot analyze the unsteady flow directly, we need to convert the unsteady flow to equivalent steady flow. So for that, let's see, before going to those, the types of surges. So when you sudden operate the gates, if the water level is going to be rises, if water level rises, while operating the gates suddenly, now you see, if water level rises, it is known as a positive surge. And if water level falls, we call it as a negative surge. Okay. So while operating the gates, if water level is going to be rises, we call it as a positive surge. And if water level falls, we call it as a negative surge. So generally there are two types of surges based upon the height of the surge that we'll be seeing now. So what is the meaning of this while operating the gates suddenly, sir? Now, you may close the gate suddenly or you may raise the gate suddenly. Now, what if I am going to close the gate partially suddenly? Suddenly you close the gate partially. See, don't close the gate completely or don't lift the gate completely. Okay. Let's see. With this, you can understand. Positive surge moving downstream. So as I said, I mentioned you, as the surges are unsteady in nature, the fundamental equations of fluid mechanics cannot be used directly. Because all those fundamental equations are for the steady nature. Okay. So now to analyze surge, it should be converted to equivalent steady state. By, now you see this point, whatever I am saying, by equivalent steady state, by means, see sir, okay fine, you are saying it's unsteady nature, so I cannot analyze. So how can I analyze? If I can convert into equivalent steady state, I can analyze. But how, sir? How you are going to convert that into equivalent steady state? So for that, let's see. And that field, this blank is going to be filled now by the explanation of this one. positive surge is going to be moving downstream. What is the meaning of positive surge? The meaning of positive surge is going to be water level rises. Think and say. The meaning of positive surge is going to be water level rises. Okay. What I say, when the positive surge is moving downstream, so positive surge means water level. So in the downstream side, if the water level rises, in the downstream side, if the water level rises, then I can say it is going to be positive surge moving downstream. On the downstream side, if I say on the downstream side, if I say water level rises, then it is going to be positive surge moving downstream side. Okay. Now, think and say when it is going to be happen. When the water level on the downstream will increase, when you lift the gate or when you close the gate. When you lift the gate or when you close the gate. When you lift the gate, more water will go to the downstream. When you lift the gate, more water will go to the downstream and water level on the downstream rises and that surge is moving towards the downstream. Yes or no? Positive surge moving downstream is by sudden lifting of gates. By sudden lifting of gates. So now you see again we assume the common assumptions. The common assumption is frictional losses are neglected. In surges also we don't consider the frictional losses and we consider as the channel bottom as horizontal. Let's see. This is a sluice gate. This is one. So initially everywhere the level of water on the downstream side, everywhere the level of water on the downstream side, you see the initial depth on the downstream, this is y1 and the velocity of flow is going to be v1. The velocity of flow means on the downstream side. I am discussing only on the downstream, not on the upstream. Okay. Now, when I suddenly lift the gate, what is going to be happen? So now you are there. If you suddenly lift the gate on the downstream side, suddenly the water level will rise. Now, if I lift the gate suddenly to this point, or if I lift the gate suddenly to this point, then the water level will rise suddenly up to this point. If I lift the gate suddenly to this point, now you see now you tell me what is the depth of flow. See, initially this is the depth of flow. Initially this is the depth of flow. Now, if I lift the gate suddenly from here, this is 1 and this is 2. Now, what is the depth of flow here? Tell me. The depth of flow is no more y1 because more amount of water will come to the downstream side or not. Now, the depth of flow is going to be y2 and no more the velocity is going to be as a y1. Sorry, v1. The velocity of the flow is going to be v2. Okay. So initially this is the 1. When the gate is going to be 1, now after some time, when you lift the gate suddenly, the water level will be rises. And once this water level rises, this rising water level will travel towards whom? Downstream, and slowly it will meet its downstream water level and reaches to its initial position. Slowly it will meet to the downstream and it reaches to the initial position. So, and this initial position up to this point, whatever this one, you see, this is a small elementary waves or not? Yes or no? An elementary waves means small waves. The meaning of this is nothing but elementary waves. A small waves are going to be travel, and this is known as a surge, my dear. What is this? Here it is going to be the surge. And while it is moving, this surge is going to be have a velocity. While it is moving, this surge is going to be have a velocity known as a velocity of a surge wave. So what is happening over here is due to sudden lifting of the gate, just next to the gate, the water level rises from Y1 to Y2, and that water level will travel towards the downstream side with a other velocity, means with a again new velocity known as VW, and finally meets the initial water level Y1. Okay. So don't think the flow is from Y1 to Y2. The flow is everywhere initially Y1. Now due to sudden lifting, the water level rises to Y2, where VW is velocity, absolute velocity of surge wave or elementary wave. We call it as a surge wave or elementary wave. Okay. Now, repeating the point again. Once the surge comes, is it steady or unsteady? Once the surge comes, then it is going to be steady or unsteady. So this is going to be make sure the flow is going to be unsteady. Initially, before lifting the gate, it is steady or unsteady. Before sudden lifting of the gate, it is a steady. And if you suddenly lift the gate, water level rises, and this surge will travel to the downstream with some new velocity known as a VW. And this VW is responsible for converting the flow from steady to unsteady. VW is responsible for flow to be unsteady. Flow to be unsteady. Now, if I want to analyze this one, can I analyze for the unsteady flow directly? No. I have to analyze it such it should be converted to equivalent steady state. Sir, how come it is going to be converted to equivalent steady states? Now the point is, who is responsible for the steady to unsteady? VW. Yes. Who is responsible for converting the steady to unsteady? VW. Now, if I neglect this VW, means if I neglect the surge, if I remove the surge, then the flow is going to be steady. As simple as that. If I remove the velocity of these waves, see, it's simply when you go in a river by means of some boat, on the next to that boat, you can see some waves are going to be travel or not. If you see in a river, if this is a boat, so next to that, you can see some waves are going to be formed. And these waves are nothing but the surge waves. Those are going to be travel along the flow, right? So they are going to be travel with some velocity, and that velocity is known as a surge velocity. Okay, surge velocity. And now you see, in order to convert into equivalent steady state, what we do is we apply a imaginary magnitude of VW opposite to the direction of surge. What I'm going to do is, so in order to neglect this, means for making it as an equivalent steady state, now this is equivalent steady state. In order to make it as equivalent steady state, okay. So what we are going to do is we apply a magnitude of VW, an imaginary magnitude of VW opposite to that direction of surge. Now you tell me, to analyze surge, it should be converted to equivalent steady state by applying imaginary VW opposite to the direction of surge. Opposite to the direction of surge. Sir, what happens if I apply this VW, sir? Sir, if I apply this VW, now you see everywhere the flow is going to be changes or not. Everywhere the flow is going to be changes because this is VW and this is also going to be VW. Now let's see. Let's see. Now the graph of or the water curve looks like this. So there is no surge over here. What is this depth? Depths are same y2 and here depth y1, and you see here depth is going to be y2 and here is going to be depth as a y1, and you see the VW is going to be 0 or not, but you see there is a V1 and you are applying VW imaginary magnitude, there is a V2, you are applying V1, and now whatever this is known as VW minus V2, because the velocities are one direction, the surge wave I am applying is going to be the other direction, right? This is VW, right? So let's assume the velocity of wave or velocity of surge wave is more than the velocity of the flow. Let's assume the velocity of surge wave is more than the velocity of the flow. So now this is VW minus VW. Here VW minus VW 0. V2 minus means VW minus V2, and this one is going to be VW minus V1. VW minus V1. So now this is a equivalent steady state. Now this is equivalent steady state. So now whatever we assume, assumptions are same. Flow is one dimensional and pressure is hydrostatic. Frictional losses are neglected. Channel bed assumed as horizontal. Channel bed is going to be assumed as a horizontal. So how I am going to convert that the unsteady to the equivalent steady state? By applying a imaginary value of VW opposite to the direction of a surge. Now I can do the analysis for this one. Okay. Now you see whatever the distribution here. Pressure distribution is hydrostatic, but this time this is FH2 along the direction of flow, FD resisting FR, and there is going to be the hydrostatic force. This is FH1. And once I know this, then you can apply all the equations. Okay. Then you can apply all the equations now, you see. So see, just you need to know what is what, that's it my dear. You don't go beyond this one, please. You don't go beyond this one. See what is happening here due to this VW, it is unsteady. If I remove the VW, that is steady. So what I did is I applied the imaginary velocity of VW. So that this is VW minus V2 and here is going to be VW minus V1. Now I can apply. Now once I do this, then I can apply the equivalent means the equations. So now from continuity principle, you know that Q is nothing but A1 V1 into A2 V2. So now here A1 into VW minus V1 is equals to A2 into VW minus V2. So assume unit width. Which means B is equals to 1, which means we can write Y1 into VW minus V1 is equals to Y2 into VW minus V2. So VWY1 minus V1Y1 is equals to VWY2 minus V2Y2. Let's take the VW outside. Let's take the VW outside. So now, you know the VW. So VW can be written as a Y2 minus Y1 is equals to V2Y2 minus V1Y1. Okay. Now finally, what is the velocity of the surge wave? V2Y2 minus V1Y1 by Y2 minus Y1. This is from the equation from the continuity principle, my dear. So what is the here VW? VW means velocity of the surge wave. And for that VW, you require V1, Y1, V2, Y2. You require V1, Y1 and V2, Y2. But you tell me, do you know how much water level is going to be rises? Do you know this velocity? Do you know this velocity? Even I can find out the Y2. Do you know the velocity? No, you don't know. So as you don't know, now what I'm going to do is I'm going to use one more principle. I'm going to use one more principle known as a linear momentum principle, because once I have taken this one, now I can apply the linear momentum principle. Apply linear momentum principle. So what is the linear momentum principle here? So now you go back and you check what are the forces acting along the direction of flow. Now FH2 plus FD minus FR minus FH1 is equals to rho Q into V2 minus V1. Yes. So this is going to be the V2 minus V1. V2 minus V1 means here the V2 is going to be VW minus V1. VW minus V1 minus VW minus V2. FD 0 and FR is also going to be 0. And FH2 minus FH1 is equals to rho Q into VW minus VW will be gets cancelled. Then V2 minus V1. V2 minus V1. Okay. So now from equation 2 and this is equation 1. I am going to solve directly from 1 and 2. From 1 and 2. What I got to know here is, I'll write one more way here. This is going to be written as rho Q into, this is going to be Q, right? And you know Q is nothing but Y into VW minus V1. Okay. I can write this one. Just simply I can write this one. A1 into VW minus V1, right? So now rho into Y1 into VW minus V1 into V2 minus V1. Okay. Because you can substitute this one into 1. Now from 1 and 2, I am not going to find out this. I am not going to derive it completely. So from 1 and 2, I can write down directly as VW minus V1. VW minus V1 is equals to root of G by 2 into Y2 by Y1 into Y1 plus Y2. Y2 by Y1 into Y1 plus Y2. So see, I have eliminated one thing. Which one I eliminated? Which one I eliminated? I eliminated V1. Sorry, I eliminated V2. Because you know, I know V1, I know Y1. When I rise, I can find out Y2. But I don't know the V2. I don't know the V2. So what I have done is, first I apply the continuity principle and I got this. But still there is a V2. I don't know the V2. As I don't know the V2, I applied the linear momentum principle, and by using both 1 and 2, this is a 2, this is equation 2. By using both 1 and 2, I have removed that V2 and I have written this equation in this form. And this form okay. And this form is very important. So This is the only equation that I'm going to ask you to remember in surges if they give a question regarding to the surge. So why? Because what is this VW? In order to find out the velocity of the surge wave, I applied the continuity principle and I applied the continuity principle and I applied the linear momentum principle. So from there I got this one, VW minus V1 is equals to root of G by 2 into Y2 by Y1 into Y1 plus Y2. Forget about the derivation. You don't require the derivation. After all, this topic is not that much important also. So forget about that derivation. Okay. So what I want you to look over here is this V1 is this equation we get by solving it, sir? Yes. Sir, how you put imagine Y1 into VW minus V1? Remember, you carry what I have written over here. This is nothing but discharge. Yes. And I can write the discharge over here. Yes. So now that's about this VW minus V1. So why I got this VW minus V1 is because you see this is VW minus V1 because the flow is moving downstream, then the imaginary velocity I am applying is going to be the upstream. Okay. So this is imaginary velocity VW and this is going to be the V1, or else there is a one more form. Just wait for that moment. I am going to say that. And based upon this, there are two type of surges. Based upon the height of the surge, So based upon the height of the surge, we have two type of surges. So here the height of surge Y2 minus Y1. Two type of surges would be there. Types of surges. That we'll be seeing. It's already 8:55. So that we'll be seeing after the break. Have a break of 15 minutes and we'll start our session at 9:10. And probably we'll complete the surges today. And if there is any remaining small topics that we can discuss tomorrow also, but most possibly we'll complete the syllabus now. Okay. So don't worry about that. And I hope you are able to understand the topics well. We'll have a break. Now let's have a break of 15 minutes. Please have a break and we'll come back. Now let's coming back. Okay. So now coming to the types of surges, my dear. There are two types of surges. Small surge. So when do we call it a small surge? Is if y2 minus y1 is less than y1, very less compared to the y1. If y2 minus y1 is very less compared to the y1, so then we call it as a very less means a small surge, which means height of surge is very less and insignificant. Then we call it as a small surge. The example is waves produced by dropping a stone in pond or stream of water. And second one is a large surge. Second one is a large surge. So when do you say the large surge, sir? When do you say large means if y2 minus y1 is just less than y1 and considerable, then we say it as a large surge. Then we say it as a large surge. Okay. So now, my dear, where do we see this one, sir? Examples are going to be tidal waves. Examples are going to be tides or tidal waves. So whatever the waves produced by dropping a stone in pond or river are nothing but small surges, and large waves are going to be the tides. Okay. Now, based upon the type of surges, now the last and most important concept, celerity of wave. Celerity of wave. Sir, can surge height be equals to y1? No, sir, it won't be. Think about that. Wave height is small and the depth of water is very large, right? Celerity of wave is represented with c. And what is the celerity of wave, sir? This is a relative velocity of surge wave with initial flow velocity. Relative velocity of a surge wave with initial flow velocity. Okay. So what is meant by celerity? Celerity means the celerity means initial flow wave, means what is the velocity of the surge wave with respect to, means relative, means with respect to the initial flow velocity. See, the resultant velocity is different and relative velocity is different. Yes or no? When two bodies are moving in the same direction, then what is the relative velocity of one body with respect to other body? And we have heard about in physics sorry. We have heard about in physics, if two trains are moving in a same direction with the same velocity, then you can see the person in the other train as a constant body with no movement. Yes, which means the velocity of you related to the other person is zero, because both the bodies are moving in the same direction. So if two bodies are moving in the same direction, then the relative velocity is going to be difference of those velocities. Yes or no? So now in the case of the downstream side, you see this is a surge moving on the downstream. So the VW direction is VW and this is going to be the V1. Both are moving downstream or not? Both are moving downstream. This is not an imaginary velocity. This is the actual velocity of the surge wave. Then what is the relative velocity? the relative velocity C is equals to VW minus V1. VW minus V1. VW minus V1. Okay. So see, VW minus V1, this is a relative velocity. As if both velocities are in the same direction, then the relative velocity is going to be VW minus V1. Now, somewhere we have seen this VW minus V1, right? What is VW minus V1? Root of G by 2 into Y2 by Y1 into Y1 plus Y2. Okay. So C is equals to root of G by 2 into Y2 by Y1 into Y1 plus Y2. This is for the large surge wave. This is for the large surge wave. Because what is C? VW minus V1 or not? For the large surge wave, we are going to take it as. And for small surge wave, again, the C is nothing but here VW minus V1 is equals to R. Celerity is equals to root of G into D1. This is based upon the Lagrange, and this is for the small surge. This is for the small surge. Because in the case of the small surge, Y2 minus Y1 is very, very, very less than the Y1. Yes or no? And if you go for rectangle, my dear, for rectangle, you know, D is nothing but Y. D1 is nothing but Y1. So C is nothing but root of GY1. Root of GY1. Sir, how you got this one as a root of GY1, sir? Now have a look. Sir, how come we assume VW is greater than V1 and V2? Sir, if you assume VW less than V1 and V2, that is also not a worry, because see, once the unsteady nature comes into existence, the velocity of that wave is more than the any other velocities. That's the reason why we take VW greater than V1 and V2. Okay. Now, root of GY1. So this is for the small. This is for the small surge. This is for the small surge. So in the large surge wave, just you see in the same equation, see in small surge, I am taking Y1 and Y2 both are same, almost same, because the Y2 minus Y1 is very, very, very less than the Y1, so insignificant. If I take Y1 and Y2 both are same. Now please substitute. If I take Y2 as Y1 will get cancelled. Y2 as Y1 plus Y1, 2Y1, and 2 gets cancelled. Then what is remaining? Root of GY1. If you substitute this Y2 as a Y1, then that is a small surge wave. If you substitute this Y2 as Y1, that is going to be the small surge wave. Okay. So what is the celerity? For a small surge, root GY1. For a large surge, it is going to be root of G by 2 into Y2 by Y1 into Y1 plus Y2. And what is the actual definition of celerity? VW minus V1. In examination, if nothing is mentioned, yes, this over the total, this root is total. The root is going to be over total. So now you see, does this just looks like note? In exam, if nothing is mentioned, always use celerity of small surge. Okay. So generally in examination, they will mention that due to rise of the gate, the water level increases by this percentage. Due to sudden rise of the or sudden lift of the gate, the water level increases by this percentage. If they mention the difference between Y1 and Y2, my dear, then you must have to use that. But if they don't mention that, then you always go with the small surge. If they don't mention whether it is small or large, you always go with the small surge. Okay. Now, this surge, again, if you look over, this C is nothing but a root of G into D1. Yes or no? And does it just similarly looks like what is a Froude number? Froude number V is equals to, means FR is equals to V by root GD. And whenever the Froude number is equals to 1, then that is going to be the critical flow. And whenever this is going to be VC, then what is VC? VC is equals to root of GD. Let's take it as equation number 1 and let's take it as equation number 2. From 1 and 2, can I say the celerity is nothing but VC? The celerity of the flow is nothing but critical velocity of the flow. So the last note point here is the celerity of wave is the critical velocity of the flow. Critical velocity of the flow. So the celerity of the wave is going to be critical velocity of the flow. Keep that in your mind. So now this is about the celerity. What is celerity? That's the relative velocity of the surge with initial flow velocity. And what is that? Root of G by 2 into Y2 by Y1 into Y1 plus Y2. And for the small surge, root of G by 1. If they don't mention anything, you always go with the small surge only. And you know this is root of GD1, right, from the Lagranges. Okay. So you know that for the critical flow, Froude number is equals to 1. And whenever I say Froude number 1, then VC is nothing but root GD. From 1 and 2, I can say the critical flow velocity is nothing but the celerity of the wave. Okay. So, sir, whatever the analysis I made is for whom? Positive surge moving downstream. Now, the similar way I am going to do with the positive surge moving upstream. Now, you see. B. Positive surge moving upstream. See, what is the meaning of positive surge moving towards upstream? So on the upstream side, water level should rise and it move towards the upstream side. Yes or no? So now you tell me what is going to be happen here is by sudden closure of gates. By sudden closure of gates. Okay. Now you see. Okay, so now if you observe, positive surge, my dear. So what is the physical significance of the celerity, sir? The physical significance of the celerity is, you see, if I know the celerity, I can say the critical velocity of the flow. If I know the celerity, I can say what is the critical velocity of the flow, and based upon that, if the velocity of the flow is more than celerity, subcritical. If the velocity of the flow is less than celerity, supercritical. Okay. Yeah. Now you observe over here. See, initially this is the sluice gate. So as it was gate, now you see this is the initial water level. This is the initial water level whose depth is going to be y1. Now this time I am discussing about upstream side. So the velocity of flow is going to be v1. Okay. Now this is 1. This is 1. Now if I close the gate, partially, so don't close it fully. If I close the gate partially. Now when I close the gate, now what happens? So the flow is happening. Now if I close the gate, the flow will get obstructed and the water level will rise. Yes or no? Now the water level will rises. Now the water level will rises and move towards whatever this is y2. So once this water level is going to be rises, is it happening gradual or sudden? Sudden. So as I close the gate suddenly, water level impact suddenly rises and it will travel as a surge. Now this is an elementary waves and it will travel towards the upstream. See, whatever the surge wave you can see, these are the elementary waves or not. In this multiple waves would be there. In this multiple waves would be there. And whatever the top wave, at the top there is a higher velocity compared to the lower velocity. Means here, bottom is going to be the lower velocity. So keep that in your mind. The surge consists of multiple small waves with high velocity of waves at the top and low velocity at bottom and low velocity at the bottom. So the surge consists of multiple small waves with high velocity of waves at top and low velocity at the bottom. Okay. Now, now you see, now here the surge is moving towards upstream or downstream. The surge is moving towards the upstream with the velocity of VW. The surge is moving towards the upstream with the velocity of the VW. It is not moving downstream. Now this time the surge is moving upstream. If the surge is moving upstream, then you see, go back and tell me if I want to make it as a, if I want to make it as a C, here the velocity is going to be V2, and if I want to make it as a equivalent steady state, then I need to apply an imaginary velocity opposite to the direction of flow. This is VW. Here, this is VW. Here, this is going to be the VW. Yes or no? Now for the equivalent steady state, let's see that. For the equivalent steady state, now you can observe whatever this depth, here it is y1 and this depth, here it is going to be y2. Now you tell me the imaginary velocity is going to be in the direction of the flow or not. You see normal flow, surge move towards upstream. Normal flow, surge move towards upstream. Now the imaginary velocity will be towards downstream or not. Normal flow, surge, imaginary velocity. Both are in the same direction. Then what is this velocity over here? Please tell me. VW plus V1. VW plus V2. That's it. Apply the continuity principle. Apply continuity principle. Now, y1 into VW plus V1 is equals to y2 into VW plus V2. VW plus V2. So similarly, you please derive this one. So now VW Y1 plus V1 Y1, VW Y2 plus V2 Y2. So now if you say these values are, if you take the VW Y1 on the other side, then now VW is equals to V1 Y1 minus V2 Y2 by Y2 minus Y1. Yes, or I'll take it as negative of V2 Y2 minus V1 Y1 by Y2 minus Y1. This is VW. This is going to be the VW. See, does this equation is exactly similar to the equation over here? This is V2 Y2 minus V1 Y1 by Y2 minus Y1. And here V2 Y2 minus V1 Y1 by Y2 minus Y1. But what is the sign? The sign represents, you see, that is a positive surge moving downstream. This is a positive surge moving upstream. So whether the surge is moving downstream or upstream, the magnitude of VW means the formula is same, but with a change in the magnitude, Okay. Now, if gate closes completely, then V2 is equals to 0. When V2 is equals to 0, then VW is nothing but V1 Y1 by Y2 minus Y1. When gate closes completely, see, if the gate is going to be closed completely, on next to the gate, there is no flow, right? When there is no flow, flow will stop and the velocity just next to the gate is going to be 0. So I am closing this gate partially now, you see. So this is V1, VW. Now similarly, from continuity and linear momentum principle. From continuity and linear momentum principle, you are going to see, observe, why I got VW minus over V1 here? Because this is going to be VW minus V1. Yes or no? I got VW minus V1. So similarly, now what I got is the VW plus V1, right? So if you substitute VW plus V1 is equals to root of G by 2 into Y2 by Y1 into Y1 plus Y2. The same equation. See, equations are going to be same. Only the change is going to be the sign. So in the case of the positive surge moving downstream, VW minus V1. In the case of positives moving upstream, VW plus V1. So now, what is the celerity, sir, here? Celerity. Here the celerity is, see, in this case, surge is moving upstream and actual velocity is moving downstream. Then the relative velocity is nothing but VW plus V1. So again, you know that C is equals to G by 2 into Y2 by Y1 into Y1 plus Y2. This is for the large surge, and root of GY1, this is for the small surge. What is the only change that you are observing? In the case of the positive surge moving downstream, see what is here? In the case of the positive surge moving downstream, what is celerity? VW minus V1. Just you remember these directions, right? You remember these directions, then you can understand everything. See, what I finally want you to understand is that celerity. That's it. If you understand that celerity, you can find out the values. When the flow is moving downstream, flow V1, positive surge, VW, both are in the same direction. Relative velocity is VW minus V1. Now, when the surge is moving upstream, flow is moving downstream, V1, and surge is towards upstream, VW. Both are different direction. Relative velocity is positive. VW plus V1. And for the large surge and the small surge, in both the cases, the magnitudes are going to be same. I hope you understood. So I did not give you the derivations for this case. I have just given you the formulas, and the last note point over here is negative surges are highly complex in nature. So we don't analyze the negative surges. Sir, what is the negative surge, sir? Sir, if you open the gate partially, if gate close abruptly, partial. If the gate is going to be closed abruptly, partial. You see, initially this is the water level, and on the downstream side, this is the water level. Yes or no? Now, if I close the gate abruptly, and that too partial, you are not going to be close it fully, you are going to close it partially. So then what is going to be happen? On the upstream side, you can see the positive surge moving towards the upstream. This is a positive surge moving towards the upstream. On the downstream side, now this is the gate, right? Now this is a negative surge moving towards the downstream. This is positive surge and this is a negative surge. Okay, positive surge, because compared to the initial depths, Y1 and this is the Y1, you see when you suddenly close the gate, from here to here, when you suddenly close the gate from here to here, what you can observe is on the upstream side water level rises, positive surge. On the downstream side water level falls, negative surge. So forget about the negative surges. We don't deal with the negative surge. Negative surges are highly complex in nature. That's not at all useful. See, most of the people may think that I am going first for these surges, but I'm telling you, this is very least important for your examination. And the concept that you need to know, understand is the celerity. That's the only point. At the end, the handful of equations you require in this point is, you need to understand what happens when I lift the gate. Okay, positive surge will move towards downstream. What happens when I close the gate? What happens? Positive surge will move towards the upstream. Okay. Then what is the celerity? On the downstream, both are same direction, minus. On the upstream, opposite direction, plus VW plus V1. Upstream, VW minus V1, downstream. So if you have understood this, I hope you can solve any problem based upon this. So I'll give you one question first. Okay, so you please record this question. I did not attach this question, so I want you to solve this. Now, question: a 2-meter wide rectangular channel has a flow with a velocity of 2 meters per second and depth of 1.3 meters. Depth of 1.3 meters. Okay. So now the rate of inflow the rate of inflow at the upstream and is suddenly increased. Suddenly increase to an extent that the depth is doubled in magnitude. That the depth is doubled in the magnitude. Estimate the absolute velocity of the resulting surge. The absolute velocity of surge. The absolute velocity of a surge. So what is the absolute velocity of the surge? I am asking you. So now this question, understand it clearly first of all. So what is the width of the river? 2 meters. And initially the flow is happening with a velocity c. Initially the flow is happening with a velocity, means with a depth y1, how much? 1.3 meters. And velocity v1, 2 meter per second. Now the rate of inflow at the upstream end is suddenly increase. See, you see the meaning of suddenly increase. When the rate of inflow is going to be suddenly increase, if the gate is going to be rises suddenly, or if suddenly increases when the gate lifts suddenly. So inflow increase suddenly when gate lifts up suddenly. When the gate is going to be lifts up suddenly, see on the upstream side, initially this is 1. So everywhere the water level is going to be like this. Now we are going to raise this gate on the upstream side. Initially now this is going to be final. So what happens is the upstream depth is going to be increases. Yes or no? Now this is the surge you are going to see. Is it a positive surge moving downstream or upstream? Downstream. Positive surge moving downstream. This is V2. Okay. So now I am asking you the absolute velocity of the surge. I hope you understood what is happening. The meaning of rate of inflow at the upstream end is suddenly increases, means when you lift the gate, then only it is going to be suddenly increase. So when you lift the gate, then positive surge moving downstream. Positive surge is going to be moving the downstream. And what is the y2? To an extent that depth is doubled in magnitude. The depth is doubled in magnitude means y2 is equals to 2 times of y1, which means 2 into 1.3. What is this? 2.6 meters. And initial velocity is v1 is given. Now what I am asking you is vw, right? Yes. So you know that vw here from the celerity concept. So here the surge wave Vw and initial velocity V1. Surge wave celerity is nothing but Vw minus V1 is equals to root of G by 2 into Y2 by Y1 into Y1 plus Y2. Y2 by Y1 into Y1 plus Y2. Yes. So now you tell me in this case, yeah. So G by 2 into Y2 minus C. Why I am taking this as a sudden increase when lift gets suddenly. Now Why I am taking largest charges are? Because you see, my dear, what is y2? Y2 is 2 times of y1, which means that the difference is going to be too much or not. If they wouldn't have given y2, I can take it as small such. Now, what is VW? VW minus 2 is equals to root of 9.81 by 2 into y2 is nothing but 2.6 by 1.3 into 1.3 plus 2.6. So this VW, now if I solve 1.3 plus 2.6 into 2 into 9.81 square root of answer plus 2. So this velocity of such wave is going to be how much? 8.185 meter per second, and we can write 8.19 meter per second. So what is the velocity of the surge wave? 8.19 meter per second. Okay, 8.19 meter per second. Now, I hope you understood this. So when you understand this, and now you see, I will add one more question over here. This is, I hope you understood or not? Here upstream, see what is the meaning of this one? See, for this flow, this is going to be downstream and this is going to be upstream. But the meaning of upstream means on the top of you, the water level rises. So that's it. How the water level rises? If I lift the gate on the upstream side of this one, now I am considering about this portion. Think when you are here, your next, your upstream, this one, your downstream is this one. Okay. Now, so now I will go with one more point here in this question B. You see the rate of inflow at the upstream is suddenly increased or not? Now it is going to be unsteady in nature. Now what is the new flow rate? What is the new flow rate? Which means, you see, what is a new flow rate? See, when you rise, then the depth and velocity both are going to be changes. Initially V1 Y1. Now, what is a new flow rate? New flow rate means Q2 is equals to Y2 into V2. Y2 into V2. Now, do we know this V2? I don't know. Do we know this V2? I don't know. So as I don't know the V2, now what I do is from equivalent steady state, I don't want you to remember the formula. If you do remember the formula, fine. But from equivalent steady state, you can say what is the equivalent steady state here? Both are in the same direction or not? See, now from the equivalent steady state, then you know that Y1 into VW minus V1 is equals to Y2 into VW minus V2. I want this V2, my dear. I want this V2. So now, what is Y1? Y1 into VW 8.19 minus, what is V1? 2 is equals to Y2 means 2 times of Y1, 8.19 minus Y2. Y1 will get cancelled. So from this, what is V2? 8.19 minus 2 by 2, 8.19 minus answer. So the V2 is going to be 5.095 meter per second, and new flow rate is equals to 2.6 into 5.095. 13 point, yeah, okay. So they have given the width also, right? Sorry. I'm sorry. They have given the width also. So what is the width given? The width is given as 2 meters, right? Okay. So BY2 into V2, 2 into Y2, 2.6 into 5.095. So that's going to be 26.49. That is going to be 26.49 meter cube per second. So when I go for the new means I am going to increase the rate of flow. So then definitely, obviously the discharge increases. That is the reason why it's unsteady, right? What is the meaning of unsteady? Flow rate changes. So when I lift the gate, the flow rate increases. And how to find out that increase in flow rate is nothing but Q2 is nothing but A2 into V2. Q2 is nothing but A2 into V2. So now, in order to find out the V2, I am going to take the help of the equivalent steady state. Sir, where is B over here, sir? The B is nothing but here. The B will get cancelled. The width will get cancelled initially itself. Okay. So I hope you understood this. Give me a minute, please. You try to solve this question. The only one question left over. Easy. Okay, fine. You please solve this first. You please solve this first. This is our previous ESC. Previous ESC question. Please try to solve this. Now you can see this question. Before passage of a surge, the depth and velocity at a flow section are 1.8 and 3.72. Before passage of the surge means initially the depth is 1.8 and velocity is 3.72 meters. And after passage, they are 0.6 meters and 7.56 meters per second respectively. So after passes of the surge, they are going to be the 0.6 meters and 7.56 meters. What is the meaning of this one, sir? Compared to before, after the depth is going to be less. Compared to before, after the depth is going to be less. Yes or no? When it is going to be happen? You know that here Y2 is going to be 6 meters and V2 is equals to 7.56 meters. Yes or no? As Y2 is less than Y1, water level falls. When the water level is going to be false, then this is going to be a negative surge. When the water level is going to be fall, this is going to be a negative surge. Okay. So now let's see. And when this is going to be happen? When this is going to be happen? So before passage of the surge, the depth and velocity of flow section are 1.8 and 3.72 per meter per second. And after passage, they are 0.6 meters and 7.56 meters respectively. Respectively. This is a negative surge traveling towards the downstream. Yes. So this is a negative surge. Now initially the depth of water is going to be Y1 and it is going to be moving with a velocity of a V1. Now After the passage of surge, the depth is going to be 0.6 and velocity is going to be more. So when it is going to be happen, if you close the gate abruptly, initially this is the gate level 1. Now if you close the gate abruptly, this is going to be 2. This is the water level. So this is a negative surge just now I have mentioned. And whatever this depth I'm giving you, what is this depth? This is V2. So now the surge is going to be traveling towards downstream or upstream. The surge will travel towards the downstream. This is VW for the negative surge. So what I want is this VW only, the speed of the surge. See, now I have everything with me. VW is there, V1 is there, everything with me. Now apply for the equivalent steady state. For the equivalent steady state, then I have to apply VW opposite to this. Yes or no? For the equivalent steady state, I have to apply the VW opposite to this. Am I correct or not? Now, if you observe, what is this over here? From equivalent steady state, simple, see, same, the analysis is going to be same, but they are going to be quite complex while you are using the momentum principle. So that's the reason why I have given you the V2 also. Now, from the equivalent steady state, now whatever this is VW here. This is VW. So what is the net velocity over here? VW minus V1 into Y1 is equals to VW minus V2 into Y2. Okay. Now I want VW. So let's take the VW terms on one side. VW into, so Y2 minus Y1 is equals to V1 Y1 minus V2 VW into, yes, Y2, okay, V2 Y2 minus V1 Y1. So what is VW, sir? V2, what is V2 given? V2 is going to be 7.56 into 0.6 minus 3.72 into 1.8 by Y2 minus Y1, 1.8 minus 0.6. Please solve this. So if you solve this, this is going to be like a 7.56 into 0.6 minus 3.072 into 1.8. So 3.72 into 1.8. See, let's observe this 1.8 is a 3 times of a 0.6, right? Obviously, the value is going to be negative. Why, sir? Because this is 0.6. This is 0.6 and this is going to be 3.7 to 1.8. 1.8 is nothing but 0.6 into 3. Yes or no? So this value is going to be negative. I can obviously eliminate these two. Now, if I want to solve this one, 7.56 minus 0.6 minus 3.72 into 1.8. So I can write this equation as, okay, yeah, further, as I don't have a calculator, I will write VW is equals to 7.56 minus 2.6 minus 3.72 into 3 into 0.6. I'll rewrite this one by 1.8 minus 0.6 are 1.2. Take out 0.6 outside, which means 7.56 minus 3.72 into 3 by 1.2. 0.6, this is going to be 2. Now 3.72 into 3. 3.72 into 3, 3 to 6, 7 3 is 21, 3 3 is 9. So it's going to be 11.16. So 7.56 minus, so 0. So then 5 and 3 minus 3.50 by 2. What is the answer over here? Where will it come? Yes. Sorry, this is 6, right? This is 6. Yes. This is 6. So minus 3.60 So what is this value? 1.8 meter per second. The answer is going to be minus 1.8 meter per second. Why it is not minus? Where from? Have we done anything wrong? Okay, fine. Yeah. So this is a 0.6 minus 1.8. I'm sorry. This is minus 1.2. This is minus 1.2. So minus. So this is going to be minus value. Okay, so the answer is going to be plus 1.8 meter per second. So this is the final answer. Negative surge, for the negative surge, your answer is going to be 1.8 meter per second. I'm sorry, while I was substituting this, so y2 minus y1, y2 is 0.6 and y1 is going to be 1.8, is 1.8 meter per second. Where is complexity? The complexity will come when you are going to analyze the linear momentum principle. Okay, so with this, we have completed this question. So this is one of the previous ESC question. Why I have taken this question is to make sure the negative surge, so you can understand. While you are applying the continuity principle, both are same. When you apply the continuity principle, both are same. Now, you please solve this question. This is a homework for you. I'm going to attach this. And only one thing is left over. The only one thing is left over is so wave patterns are due to the surges. So that's a 15 to 20 minutes topic that we will be discussing tomorrow. So tomorrow we'll be discussing some first 15 to 20 minutes regarding to the wave patterns, and then we'll go for the dimensional analysis. So in the tomorrow first 20 minutes we complete the wave patterns. With that we'll complete the entire open channel flow, and the remaining portions dimensional analysis will be discussed in the tomorrow session. Okay. Yes. It's already been 10:10. So I'll take the doubt clearing session also tomorrow. I'll take tomorrow. So whatever the doubts you are having so far, I'll take that tomorrow. Tomorrow I'll take the class up to 9:40 or 9:45. So from there I'll take some 30 to 45 minutes as doubt clearing sessions. So tomorrow we'll be discussing those. And if you still have any doubts, you can follow pawan.isfaculty@gmail.com. And Insta ID is so you can follow me there or you can mail me there. And I hope there are some WhatsApp groups are going on for the other batches. I don't know whether you have a WhatsApp group or not. So you place you can go through the WhatsApp groups also. So one of the means civil. I hope that a civil group is there. You people are there already. So apart from that, some WhatsApp groups are going on. AS Civil 1, AS Civil 2, something like that. Recently, I have a notification. I got that, and I have been added over there. So that because in all the groups, the number of people are piling up. So in one of the group in Telegram, it's like 6,000, 7,000 people. Means as a number of people are piling up, it is not possible for me to go and to go through the each and every question. So if you have any doubts, you please mail me this. You can message to this number. So that will be more convenient for me. And if you mail, means if you WhatsApp to this, then I can receive your questions and I can answer there. So that's all for today. And we'll see the remaining things tomorrow. I hope we'll be discussing. Yes. Yes, tomorrow we'll see the doubt clearing session also. So that we'll see tomorrow. Up to then. Have a nice day. We'll meet tomorrow.